Good morning. In my last session on electric fields and potential, I was essentially looking for the answer to one question. Can I get Mathematica to show me a vector field similar to those shown from our textbook? Our textbook, Sir Wave Wheel's College Physics, though now we are using 10th edition, describes electric forces and electric fields in Chapter 15, though it doesn't go on to describe the simpler concept of electric potential until Chapter 16. But what I wanted to see Mathematica reproduce was right here in section 15.5 on electric field lines. Electric field lines, it says, has these two properties. One, the electric field vector is tangent to the electric field lines at each point. Now, I have been able to reproduce that phenomenon with great success using Mathematica's stream plot and stream density plot. I was able to get the electric field vectors tangent to the electric field lines at each point. But it also says 2, the number of electric field lines the number of field lines per unit area through a surface perpendicular to the lines is proportional to the strength of the electric field in a given region. Now that is not what happens here with using the stream plot. If you look at the density of the lines out here at the edge of the graph, it's roughly the same as the density of the lines in here at the inside of the graph. So the stream plot function in Mathematica adds extra field lines to fill up the space. On the other hand, the field lines introduced in Sir Wave Wheel's College Physics can only either begin on a positive charge or end on a negative charge. With the stream plot, we have a couple of these lines coming out of the actual charge, but then we have additional lines being added as we go out, coming out, say, from here, and then here's one, here's one, here's one, here's one. So I'm not sure that I'm going to actually be able to get Mathematica to show me the field lines. I can get a stream plot, which does a nice job with the tangents, but the actual getting the number of field lines to match the density of the electric field. I'm sorry, let me start over. Getting the lines to point in the right direction is not a problem, but getting the density of the electric field lines to be equal to the magnitude of the electric field. The stream plot function doesn't do that. It only gets you the direction, not the density. Now, besides the fact that this particular function, stream plot, doesn't quite do it, I also have a vague feeling that it might be impossible in principle to create a two-dimensional graph that actually does the job. Why is this? Because I think the density of field lines in 2 dimensions doesn't drop off at the proper rate for point charges. Namely, because if I want to find the density of those field lines at a given point, I'm going to draw a circle in 2 dimensions. The trouble is the density per unit area, I think that is flux over area, is not going to be found by taking the number of field lines divided by the circumference of the circle. Rather, the electric field line density will be found by accounting for, divided by area, will be found by accounting for all of the field lines coming out, which is proportional to the charge enclosed divided by epsilon naught, divided by the area of the sphere for pi r squared. Here's the trouble. The regular distribution of field lines coming out of a piece of paper are not going to be the same as the regular distribution of field lines in 3-dimensional space. Consider, for instance, a tetrahedron. We have and let's say we have from the center radiating outward in 4 directions towards the corners, the 4 corners of that tetrahedron. I think we can all agree that that is a uniform distribution of field lines. However, if I try to go and capture those field lines in a plane, I can either capture these two, or I could capture, well, if I drew the other paper going in the other direction, I could capture these two, but but you can't capture all 4 of the field lines in the same plane. That being said, I can go out to Wolfram's Demonstrations Project website and see that some effort has been made to create electric field diagrams for multiple charges. Looks like this thing, I'm guessing that this, yes, that moves. So I can move that charge wherever I want it. Now it appears here that the field lines appear at first with lots of squiggles, and then it recalculates to produce a smooth image. Right now we have charge Q1 at +1, charge Q2 at -1. Let's go ahead and move that to make that +1 as well, and see how that changes the diagram. For me, that was about a 2-minute wait before the image cleared. Now I'm seeing that this still does not quite meet the criteria that was described in our textbook. It said in the textbook that all the electric field lines should either start or end on start on positive charges or end on negative charges. These are all starting on positive charges, but this one we see right here, we have an electric field line going straight between the 2 charges. Okay, now let's try a large charge sitting next to a small charge. If this fulfills the requirements of the electric field lines in our text, the number of field lines coming from Q2, having a charge of 2, should be double the number of field lines coming out of Q1, having a charge of 1. And I see that it does meet the requirement. Q2 has exactly 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 field lines coming out, while Q1 has exactly 8, 1, 2, 3, 4, 5, 6, 7, 8. So this Mathematica application appears to do a pretty good job of building the field lines. So I wonder if I can find out if there is a Mathematica command that does this, or if it is custom code. Let's give credit where credit is due. This demonstration was contributed by S.M. Blinder, and he says it is very tricky to plot the lines of force emanating from a positive point charge and converging on a negative point charge. So, question: can I download the author code and see what commands he used? Well, one thing that's amazing is how short it is. This is it. There's nothing. This is the entire code. It's there, and then there's the appearance of the thing. So, what's it do? It looks like the Mathematica command that does the bulk of the work is contour plot. Here we have a contour plot of phi, and here we have a contour plot of psi. Alright, phi appears to be the same function that I used for electric potential, V, with 2 key differences. One, he doesn't put in the Coulomb's constant in there, and more importantly, probably, is that he is sticking an extra 0.0001 in the denominator. Now you might remember that I was having trouble with that the plots were not working the other day because the electric field went to infinity at the origin. So I'm going to try out SM Blinder's trick of simply adding 0.0001 to the radius, and do another vector plot, and this looks like good news. Earlier, let me remind you what it looks like without the plus 0.0001 by deleting those. It looks like that. But with the plus 0.0001, though this is kind of like cheating, it produces a much better looking field. Now, instead of getting an infinite vector at the center, which Mathematica has no idea what to do with, we're getting a finite vector, and then Mathematica is scaling off that one. Now the direction is going to be fine because it's still based off the x and y, but the magnitude is going to be just a tiny bit off, just a smidgen smaller than it should be. Actually, the magnitude would be infinitely smaller than it should be at the origin, although it doesn't really, it shows a little dot there, but I think the dot actually should be a really big vector. Just somehow in the algorithm they decided not to draw that vector. But it really is quite accurate as you get further and further out. I wonder if there's a way to scale the vectors. There is a vector scale command. Right now that's not quite looking satisfactory to me. Here's a thought. If adding 0.0001 to the radius made it look, made it go from unusable to not very good, what would happen if I tried adding 0.1 or 0.5 or even 2 to the radius? Now this diagram doesn't give an appropriate sense of scale, but it does give a qualitative sense that the electric field does not dissipate entirely away. It just gets smaller. When I had 0.0001 in here, you didn't get any sense of, or rather, you might get the sense that there's no electric field out here at all. But there is an electric field out here. It's just so much smaller than the electric field from here, from this point, that it doesn't show up on the scale. You might also notice that these electric fields right here coming out diagonally are a lot smaller than the electric fields coming out horizontally or vertically. Here's another issue with the vector plot, that the strength of the field line is based on the point at the origin, at the beginning, at the back end of the field line. So the back end of this field line is quite a bit closer to the center than the back end of this field line. So the strength of the electric field actually changes dramatically over the length of the mark that is used to represent that strength. Alright, this isn't quite the direction that I was planning for this video to take when I started, but I do want to just kind of discuss a little bit the meaning of this psi function. He does point out that the derivation of psi of x comma y is quite complicated in either Cartesian or spherical coordinates, and it is straightforward in prolate ellipsoidal coordinates defined by the variables. Unfortunately, I don't know exactly what that means, but there is more detail in the download. He says that prolate ellipsoidal coordinates are defined by the variable, that's a psi. I don't even know how to say that, but psi equals r1 plus r2 over r, and eta equals r1 minus r2 over r. And anyway, he sets it so that the gradient of the potential is perpendicular to the gradient of this psi function. And he derives from that this, that this psi function is 1 over psi squared minus 1 over psi squared minus eta squared q1 times psi minus eta plus psi squared eta minus psi eta squared plus the second charge times, it's similar formulation minus eta plus eta squared eta plus eta squared eta minus eta plus eta here, and plus eta psi eta squared minus, and this is minus psi eta squared. So there's subtle differences between that term there and that term there, and then transform that back to Cartesian coordinates because this is in eta psi coordinates, and then so he takes all those psi's and etas and converts them back into Cartesian coordinates, and that's what all this stuff is, all those psi's and etas, because psi was r minus x1, r minus, I don't remember exactly what it was, but in the end he does this, I think he does apply this little cheat again by adding 0.0001 to those numbers so that it does not go to infinity at the 0 point, and Mathematica can give a better representation of the answers. But this process does seem to generate some mathematical artifacts that shouldn't really be there. For instance, this line and this line, though they are perpendicular to these lines, you shouldn't actually have the electric field line coming out and meeting the electric field line of this one head on. Also, you shouldn't have this line, although it is perpendicular to all of these lines. It shouldn't be one of the electric field lines because it does not technically originate at either one of those charges. But it does effectively express the direction of the charges, or it does effectively express the direction of the field lines. So coming back to the beginning of this video, I asked, can I get Mathematica to show me a vector field similar to those shown from our textbook? Well, it looks like it can, sort of. What we've essentially done, we said the gradient of the electric potential dot producted with the gradient of some other desired function is 0. And to do this product, they went into a whole different coordinate system called the prolate ellipsoidal coordinate system. Then converting the solution psi of psi comma eta, back into the Cartesian coordinate system psi of x comma y. And then perhaps the weirdest part, we're showing a contour plot of that, what is it? It's a scalar function, psi, in order to get out a show of the electric field lines. Now, it could drive me mad trying to picture a surface which has these red lines as a contour plot. I am picturing, I think, 4 upward staircases going upward to this, coming back down to here, going up to here, leveling off, and coming back down to here. It should be possible in principle to show, instead of a contour plot, the three-dimensional graph of the functions phi and psi themselves. So I'll change the show to a graphics column. Show graphics column. And I hope to change the 2 contour plots into a list. Fail. Well, you know, I may just give this up, but the goal is just to get rid of that. Okay, no graphics column, just a plot 3D. And I don't want contour plot, I just want plot 3D. And keep in mind that I'm probably not going to finish this right now in this video. But the whole idea is just to kind of get rid of everything accept just that plain plot 3D function. I think that is all stuff for the plot, for the contour plot. So, and then bad stuff happens because I don't know what I'm doing. Alright, never mind all of that. I'll just copy and paste the psi function and put in values for the charges and positions and do a simple plot 3D. And so I find that I was wrong about the spiral staircases both going down to the center. Instead, the spiral staircases both go up and come up this way. I think it would do justice to go ahead and get rid of that 0.0001 here, because it'll probably still plot it fine. So at this point, I'm just amazed that you have to come through this weird psi function and take the gradient of this thing in order to get the electric field lines. Not the gradient, I'm sorry, the contour plot. The contour plot of this thing to get the field lines. It would be neat to be able to superimpose on this image the contour plot. Right now, we can see, it would be neat to superimpose on this the contour plot. Right now, we can see in the edge-on view that that contour line is straight, and this one that goes between the charges is straight. But it would be kind of neat to be able to see the curved contour lines that would come around. I guess they would come out like, you can see that this is almost a straight up line, so several contour lines would actually meet at that point, and this is a straight up curve, so several contour lines would meet at that point. Just for fun, let's look at it with both charges being -1, both charges being, whoops, sorry, this is a +1 and -1 charge. Here's a -1 and +1 charge. You can see on these that the contours, the level contours, are going to come around from one of these vertical columns to the other vertical column. So it's still kind of hard for me to look at these two graphs and say, and envision in what way they are basically perpendicular to each other, but that is my understanding, is that the gradient of this, call it a pseudo potential, this is the actual electric potential, the gradient of this graph is perpendicular to the gradient of this graph at every point in space. And it seems amazing, but you need to use that fact to get this nice, simple appearing electric field line plot. Well, thanks for joining me in my random musings.